All right. I'd like to welcome you all to fourth day. I'm Kevin Appert. I'm the program chair. Now let's get the show on the road without further ado. In the great tradition of FIG and SV FIG, Ting has sustained us all these many years, more often than not presenting at our monthly meetings. So I at this point, hand over the mic to him.
Thank you. Okay, now okay, this is the EP32 for Lattice Bravia kit. Okay. This, I think, probably you all have seen this ad. It's now $49, and last month it was $29, and I went out bought 2 of it. So that was really nice. Okay, this is the board, and I think I have the board here on the floor. So that's a very nice board. And it has the FPGA on this side, bunch of peripherals, and on the back there's I think a 2 megabit SRAM and 1 megabit serial ROM. So it's a very nice device, and it's powered up, hooked up to my computer through the RS-232. And this is most satisfying FPGA that I've ever used. You know, I have tried the FPGA from all big fours, and here's a little statistics: Xilinx, Altera, Lattice, and Actel. I think Actel has been sold to somebody. So they have a pretty good market share, and they have lots of FPGAs. So I have used all of them, but found that Lattice has the Lattice is the most satisfying FPGA. It is a single chip solution for SoC applications. All the other FPGAs requires more than 1 chip, because it needs memory, basically, external memory. But Lattice has enough memory to support 4th. Okay, Lattice has the cheapest development board. Most of the development board sells for $1,000, if you know. So I don't think anybody can play with them unless somebody paying it for you. And the Lattice has the cheapest development system. Of course, it's free. So all these things, that makes makes it quite interesting. So I'm just going to go through the list of XP2 Bravia kit. So it has a Lattice XP2-5E. I'll talk about that a little bit later. 2 megabit of SPI, 1 megabit of the SRAM, and RS-232, 8 switches, push buttons, 1 reset, which I still don't know how to use, and 8 status LED, very nice for demos, and the JTAG interface, and another. They also include a parallel port, a download cable, so that talks to JTAG. Okay, a little bit about the FPGA. It is one of the lower end, on the lower end of the Lattice offerings. Not the lowest, but at the lower end. So it only got 5K of logic cells, which uses what they call the lookup table 4. So it has a 4 input. All the logic cell has a lookup table, which has 4 inputs. So that constitutes the basis of the FPGA array. and it has 166 kilobits of embedded block memory. These memories are blocks inside the chip, and so you have to access them, synthesize them as blocks. And there are also 10 kilobits of distributed memory. And this distributed memory are using the logic cells for memory purposes. Each logic cell, I think, has 2 flip-flops, which you can use as memory. And so this one is the memory is distributed throughout the chip. And it has 3 DSP blocks, which is very extensive, but I didn't use it. 12 18-bit by 18-bit multiplier, which I didn't use. 2 PLLs, and I didn't use. Of course, it has many packages, and the one on this board is a 144-pin TQFP package. Okay, so this is the design software that they supply for free. You can download them for free, but you have to go get a license from Lattice to use it. So ISP, this is not level, but level starter for Windows. And it uses simplified synthesis tools. And it also uses RDEC Active HDL simulator. With the inside the system, ISP VMR is FPGA programmer. And this programmer basically talks to the JTAG port. And it also supplies you with SP2 Bravia SoC demo, which if you get the board, hook it up, and then push the reset button, and then you have a little menu coming up, tell you what some of the very basic things they can do with this chip. And it also supplies you with Lattice Micro 8, which is an 8-bit microprocessor, and with all the tools supporting that microprocessor. It's a reference design. It also has a Lattice 32 reference design, but the 32-bit is not free, I think. And it also supplies many other reference designs with the package, so you can pick and choose and follow the designs. So the design flow, basically, you use VHDL or Verilog. I have been logged into the VHDL, so I didn't even look at the Verilog. And it also has, I think, other means of input. And both the Verilog and VHDL design are synthesized using the simplified tools. And then LDEC supplies the functional simulation. So if you enter the design using VHDL and do the synthesis and simulation, you know pretty much whether this thing is going to work or not. Okay, once you get through functional simulation, what you need to do is to go through the design planner, which allows you to assign pins to your I/O. And this is, of course, very important if you want to get anything to run on this Bravia board. And then place and route, timing analysis, and finally going to the FPGA programming, and you got your chip. Okay, a few comments on this ISP level. It's extremely complex. It takes 5 gigabytes of your disk space. So the first thing I did was clean up my drive and free up. I first free up 3 gigabit. So I got the ISP level to install. But when I want to install the simulation and synthesis tool, no, your computer doesn't work. So I have to go back and throw away a whole bunch of other things to get the 5 gigabytes. So why you need 5 gigabytes, I don't know, but it's awfully complex. And the starter system has some limitation that I encountered. I can only do functional simulation, and I cannot do pre-layout and post-layout simulation. And they say, oh, your license doesn't cover these things. So, but functional simulation is all I need. That pretty much tells you everything that you have to know. Lattice Micro 8 is, of course, very complicated, and I think I'm trying to see if I can talk to the heads of Lattice to see if I can get them to distribute the EP32. It's much smaller. EP32 is much smaller than the Micro 8. But the chip is very capable and very pleasant by itself, in spite of all the software. Okay, so I try to put EP32 on this FPGA, and the EP32. The nicest thing about this Lattice is that the logic design is stored in flash, and the block memory is mirrored in flash, so that when you power it up, it will read the RAM. Gets all its contents from the flash, so it can load up your system, and there you start to execute. Okay, so this is very nice. Other manufacturers has flash on. I think Actel uses flash, but you cannot store. It only uses flash to store your design. It cannot store your RAM or ROM. Okay, so that makes it impossible to have the one-chip solution. So 166 kilobits, which is roughly 5 kilowords, are enough to host the E4. So everything will get into the on-chip, and I don't need any external components. No external memory is not necessary. Without any effort on my part, it comes up at 50 megahertz. And I think if you work at it, you probably can push it up to 200 megahertz. So the design basically is, contains a bunch of VHDL files. EP32-chip is the top level design. EP32Q-TB, that's the test bench. And then the modules, EP32, which is core, RAM memory, which you have to instantiate it using the Lattice tool, so that it will program into flash, and when it comes back, the fresh content will be dumped into RAM memory. And UART, of course, I want to talk to something else, to a user. And the GPIO is used to operate the LEDs and switches. And just a little bit to remind you of the EP32 architecture. It has, here I implement 27 instructions, including transfer instructions, call, branch, and next, return. Memory instructions, the load using an X register, store with an X register, load X and increment the X register, store through the X and increment X. Okay, and arithmetic functions, complement, shift left, shift right, and exclusive OR. So these are the instructions Chuck gave me. So here I added the multiply step, divide step, and rotate right by 8-bit. So these instructions are very useful to implement the E4 system. And register and stack instructions, pushes, pops, push to R, pop from R, transfer to X, X transfer to T, over, drop, and no up. So these are the few instructions that you need. So if, when I synthesize it, and this is basically the report I got. I used up 1,000 logic slices, which is 47% of the logic content on chip. As I said, this is on the low end of their offering. So if you need more logic, you can go to the higher ends. And embedded memory, I used 8 out of 9. And the synthesis report says that this thing can run up to 54 megahertz without any optimization. So the E4 system, I got implemented 175 words, and all the words are 32-bit, and each word can contain 1 to 5 machine instructions, 50 megahertz execution rate, no byte addressability. So it just reads and writes in 32-bit words. And it initializes itself from the flash memory to RAM. So it runs in RAM. And the EP32, UART, and GIO, these files are moved from the Atera implementation without any change. And the only changes that I have to make is the RAM memory. And because each different FPGA manufacturer design their RAM memory differently, and then you need different tools to initialize them or to configure them. Okay, so in each of these different implementations, basically you have to change the RAM memory design according to the specification. And the EP32 chip, which is the top level, and has to be changed to reflect the changes that you made in the RAM memory VHD. So I/O pins, of course, you have to assign using the design planner according to what this Bravia manual tells you, which pins go to which signal. And the test bench, it's very nice that you can, it automatically generates a test bench for you, but you need to put in the right code in it so that it would run the whole package. Okay, and it was only after I learned how to write the test bench correctly that I got the simulator to work properly. That was about a week ago. So I'm very happy with that. Synthesis went smoothly. Simulation worked only after test bench was constructed correctly. And then I spent 2 days pondering on the system and why it didn't program. So I hook up the download cable and check the I/O pins many times. It just doesn't work. And eventually I wrote to them and said, well, why this download cable doesn't work? And finally, because Masa gave me his board, and that's with a broken cable. So you need to fix that cable. But I got two new boards. So I said, okay, I'll try another board. And I took another board and take the download cable in it, and it worked just fine. Okay, and then I open up that little connector. So there's a little board on it, and the orange line on the connector was broken. So 2 days, and I still don't know how to use the reset button properly. So every time I push that reset button, the whole system died for no good reason. I hope somebody will tell me why. But if you just unplug the power, plug the power back in, that works fine. Okay. So that's enough to take it to this meeting for the demo. And the ISP download cable. Okay, this is the with the broken cable, broken line. Okay, it's the orange line which is broken, and this is very nice. It's a JTAG cable, so all the pins on this end are loose, fly wire. So you can basically hook it up to any system which has a JTAG interface, and this cable would work. But unfortunately, this cable is on the parallel port. Okay, so I don't think anybody has a parallel port on their computer anymore. But I have to. I cannot bring the demo to bring the entire system to demonstrate the implementation and downloading and programming, because that's on my desktop. It's too much to move. But that desktop has the parallel port, has the serial port, so it was perfect for this project. And so I think from the documentation, this cable works with almost all the FPGA and the programming logic which has JTAG interface. And the system, ISP VMR, it has many support to many different programmers and programming devices. So it is very nice. I think just for that, $48 just for that cable, it's worth it. Okay, I can because I don't have the parallel port, I cannot demonstrate the programming part. The programming part, you basically hook up that cable to this port, and then you can reprogram this thing. Okay, so this is the demo. So I can only show you the eForce that's running on the kit. I can demonstrate how to turn the LED on and off, and I think for people who knows these things, if you can turn one LED on and off, and you can control the whole world. So the summary, let me see. Let me go to the. Let me do the summary first, and then go to demo. Lattice Brevia now has EP32, I think, which is much better than what they have the 8-bit clunger. And XP2 is the best, though not the largest or the fastest FPGA on single-chip SoC applications. And ISP download cable, it is a very nice device that I have seen so far. Okay, questions? Okay, let me, yes.
A USB to parallel port?
Yes. I think you can pay, I don't know how much you would pay. You can buy an USB converter, and then you can hook this parallel port to the $3? 30, okay. Yeah. Well, it's worth it. Yes.
I don't know if I asked this last time, but when you have the fourth fusion,
Yes.
the FPGA, is it static? Meaning, while it's running, can you like add new fourth instructions that you need to eventually?
Oh, yeah, right. Mm-hmm. Yeah, you can. But then if you want to add it to the flash, you need to write the code into the meta compiler. Mm-hmm. Yeah. When it's running, you can define new words. Yeah. But when you turn off the power, the new words get up. Mm-hmm. Yeah. And the chip. Yeah, yeah. The chip, they have a very specific mention on this, that you can actually write back the content of RAM back into flash. But I have not tried it yet. But it has this capability. So if you compile new words and then you say, okay, this is good, then you can do something on the JTAG to command it to store back. Mm-hmm. Not well. I don't think there's going to be any problem. I'm sorry. This will have to be done on the it's a JTAG command. Yeah, but JTAG is what they call the in-system programming. So the JTAG is always active. So when you run this board, the JTAG, you can always use the JTAG to look at the things and then send JTAG commands. Mm-hmm. Okay. Yes.
The chip had a whole bunch of multipliers.
Yes.
Extensions to
No, I have I didn't use it because the design, the basic EP32 design assumes nothing. Okay, so I have the multiply and divide step instructions, and from there I can construct all the multiply divide functions. Though I did not use the, I think if you use their multiplier, then you get yourself locked into this thing, and you cannot move around freely. Yes.
Is there any kind of a target for adding and rotating?
Beg your pardon.
In their Micro 8, is there any kind of a carry status bit?
The Micro 8 that supplies you with the assembler, and probably a C compiler. I didn't know. So you can actually rewrite the program. So the Micro 8, half of it is in the hardware and half of it in the software. So you still have to deal with the chip in two levels. It's the same with EP32. Okay, so you have the chip and you have the application. Here the application is a fourth operating system. Yes.
Some of us have bought these kits.
Mm-hmm.
Is the stuff you have done, is that available for us?
Yeah, it's available. I think for this group, I probably will give David all the source code. Okay. So I cannot. If you come to my house, I can reprogram it for you. All right, let me go to the demo. Okay, here it is already up in the code. Okay, so it comes up. If you remove power, plug the power back in, you'll get this sign out message, EP32Q version 2.03. And here are the 175 words that's implemented in this fourth system. Very simple, nothing fancy, but it makes this thing very portable. So if I go to hex mode, and what I want to demonstrate is to turn the LED on and off. Okay, turn it on. There is a port at E00. Okay, this is the I/O port. Hey. Okay. Hex E000. Okay, I was typing in O. Okay, so this is the I/O port, but what this is a bidirectional port, so I need to set the direction bit E000002. So this one defines if I put a 1 in any of this bit, the I/O bit becomes output. If it remains 0, then it's an input bit. So Here I set the lower 8 bits to output. And, well, okay. It should 0, E 0, 0, 0, 0. Oh boy, doesn't work. Okay, E 0, 0, 0, 0, 0, 0, 2. I got FF. Why? Okay. E 0, 0, 0, 0, 0, 0, 0. Okay, let me store 1 into E 0, 0, 0, 0, 0, 0, 0. I don't know.
We trust you.
Yeah, you have to trust me. Okay. F 0, 0, 0, 0, 0, 0, 2. It worked at home. E 0, 0, 0, 0, 0, 0, 2. Oh boy. It doesn't. Well, I store a 0 into the 2, but it's still replying an F. So it's still oh boy. Oh well. I can't. Okay, that's the end of demo. Okay. Thank you so much. Sorry about that. Okay, so this one belongs to Masa. So Masa, you can have it back.
It's totally done?
It's done. Yeah, it's done.